All right, hi everyone. We're going to start to look at some series. We've been looking at sequences, and so we're going to start looking at the next topic, which is series. So the first thing that I want you to do is, if you go to week 7 under handouts, you'll see a handout called Sums of Consecutive Numbers. And I want you to get that out and spend some time working on that. You'll need to actually pause the video to work on that, but I want to kind of start you off. So what you're looking for first is you're looking for any two numbers that consecutively would add up to 1, or any two numbers that consecutively that would add up to 2, and so on and so forth. Notice that there's nothing consecutive. We're not counting 0, by the way, because 0, we're going to not count that. So basically there's no numbers that would add up to 1 consecutively. And really that applies all the way through, right? You can't add 7 numbers and get 1 either. And really the same applies here. 1 plus 1 is 2, but those aren't consecutive. Consecutive numbers are one after another. So that doesn't apply here. But notice here we could do 1 plus 2. And then there would be no way to do that with 3 consecutives. Okay. Here, notice the only way to get to 4 would be 1 plus 3 or 2 plus 2, none of which are consecutive, so this is also none. The first part of this chart is kind of uninteresting, that's why I'm starting you off. But then when you get to 5, you have 2 plus 3. You can't do that consecutively, right? But for 6, you can't do 2 numbers, but you could do 1 plus 2 plus 3, and then no more after that, right? So what I think you'll notice if you just kind of play around with it is a lot of these are going to be none until you get to the higher numbers. So this could be 3 plus 4, but we can't have 3 consecutive numbers, okay, right? 2 plus 3 plus 4 would actually be 9, so that could go here, right? So I'm kind of skipping around, I know, but this would be 2 plus 3 plus 4. 4 plus 5 would work here. Notice that the even numbers don't really seem to be working out, right? And if you think about that, that should kind of make sense. They definitely aren't going to work out for 2 numbers anyway. So notice this sum could be reached by doing 1 plus 2 plus 3 plus 4, which is 4 numbers. That's why I'm putting it in that column. But we wouldn't be able to fill in any of this. Okay. So you have to kind of get to the bigger sums before this gets interesting. And so I want you to, again, like I said, I want you to pause the video and I want you to try to fill in page 2. So I'm going to show you that real quick. Try to fill in page 2 of this. But the real thing I want you to do enough of these, and it might take you a little bit. That's why I said maybe pause the video for 20, 30 minutes, something like that. But I really want you to get to these questions, okay, where we really think about maybe what patterns we have. Okay, so that's definitely the more interesting of this activity. So go ahead and pause the video, do that, and then we'll come back and talk about it. And I'll tell you kind of what answers I get on both the chart and the numbered answers. Okay, so hopefully you paused the video and kind of looked at that. I'm going to kind of just slowly kind of move this. So I think this covers maybe from 1 to 25, and you can always pause the video and kind of check your answers. That's what I would do. And then I'm going to move it up for the last little half, and again you can pause the video and kind of check your answers. So notice a lot of the spaces were none. Okay, so what I really wanted you to get is the answers to the questions. Okay, so let's kind of go over those really briefly. This is kind of like what we would do in class, but we're just going to do it virtually instead. So what patterns did you see in the chart? Okay, so here are some patterns that I noticed. In each column, every n number can be done, where n is the length of the consecutive number list. In other words, let's kind of go back to our list here. Okay. So notice that um, that you could at least do usually kind of one of them, at least one. But I kind of, after a while, I kind of went, especially for like the 1, 2, 3, 4, 5, like here, I would kind of skip ahead and kind of do some of those that I already kind of knew. So that is one thing that I noticed. So for 3, every other number can be written as a sum of 2 consecutive numbers. Okay, so basically every odd number after 3 can be written as a consecutive number, and then every third number can be written as a sum of 3 consecutive numbers after 9, and so on. So like after 9, notice that, so notice this can be done, right? And then we have 2 nones, and then this can be done, 2 nones, this can be done. And notice that pattern actually exists after a while. Notice this could be written as 4, and then we skipped 3, and then this could be written as 4, and then we skipped 3. And it actually continues on like that. So hopefully, that's why I kind of wanted you to do this whole table, and I know that took some time. I actually already kind of answered that in number 3, so I'm just going to say repeated. What about 5? Every fifth number after 15 can be written, so the pattern kind of exists. And so I made some predictions, but every multiples of 7 after 28, multiples of 9 after 45, multiples of 11 after 66. By the way, notice that this is 28 is 7 times 4. This is 9 times 5. This is 11 times 6. Okay, so it's like every odd multiple can be done, or multiples of odd numbers can be done after a certain point. Okay. Does this rule work for the even number of consecutive numbers? Okay. So notice that the rule does work, it's just off a little bit. Okay, so again, you can kind of pause this and kind of compare your answer. So you could adjust the rule by adding a constant. For example, if the number plus 2, notice 2 is half of 4. So if it's divisible by 4, it can be written as the sum of 4 consecutive numbers. Okay. And then lastly is number 8 on the list. So now use your rule to predict whether each of the following numbers can be made with 2 consecutive numbers. Okay. And so I use the rule just to predict if they would work. Okay. And so notice that that works, right? So I didn't make you fill that out in the list. Okay. But 45 should follow the pattern for 2, 4, 3, 5, 6, 9, etc. Okay. 57 should follow the pattern for 2, 3, and 6. 62 should follow the pattern for 4. And what I mean by that is the every fourth pattern, right? So here's the pattern for 4. So it works for 14, for 18, for 22, for 26, for 30, for 34. So if you keep counting up by 4s, that's going to catch 62. That's what I mean by that. 75 would be able to be found by 2 consecutive numbers, 3 or 5, and then 80 would just work for 5. Okay. So again, it's just kind of adding the multiples of that number kind of as you go. Okay, so that's just kind of something to get you thinking about the patterns and all of that. And so notice we're not only taking a pattern of numbers, but we're also adding them together, and that's actually what a series is. So let's take a little bit of notes on a series, and then when we come back in class, we're going to talk a little bit more about them. And so a series is just basically adding the terms of a sequence. And so you should have probably done it in one of your classes, one of your calculus classes or something like that. But if not, we're going to use summation notation for our series. And so summation notation uses a capital sigma. Sometimes it'll have like a little, like this, but it kind of looks like an E-ish shape. And what you're going to have is you're going to have a function over here. So we're going to call that function f of I. And then you're going to have some starting point here, and then you're going to have an ending point up top. So A is going to be your starting point, and B is going to be your ending point. We use I because it stands for iteration, so it's like different levels. And then just the symbol of sigma, that was a really sloppy sigma, but you get the point, always means sum or add them up. Okay, so let's look at some basic summation notation. Hopefully, again, this is review for you, but just in case it's not, then I want to do a couple of these. So let's say that I asked you to find the following sum. Okay, so notice this is the start, this is the end, and this means, hey, I want you to find the sum of this function. So what you'll do is begin by plugging in the bottom number, and you'll end by plugging in the top number, and you'll kind of count up from there. So you're going to take 4 times 1 plus 2 plus the next number up from that is 2, so 4 times 2 plus 2. So notice I'm just inserting the numbers into this pattern or into this function. And then 4 times 3 plus 2. And then 4 times 4 plus 2. And then I ran out of room, 4 times 5 plus 2. Okay, so I actually want to see if we can come up with these numbers, because after a while I think you'll see that there's a pattern to the sequence, and then all you're really doing is adding those up. So notice that 4 times 1 plus 2 is 6, right? 4 times 2 plus 2, that would be 8 plus 2, or 10. 4 times 3 plus 2 would be 12 plus 2, or 14. So notice it seems like to get from one term to the next, we're doing 4 more. So once you figure the pattern out, then you can you can still use your formula, but you can just hey, I'm adding 4 every time. Okay, so if I add 4 a couple more times and then add all those numbers up, I'll get 70. Okay. Note that to use our terms from last class, or the last week we were in class, which seems like forever ago, right? Each term is 4 more than the previous term, so this is an arithmetic sequence. It's just we're taking that arithmetic sequence and we're adding it up, and that's what a series is. Okay, so let's look at another one. I don't know why I'm having so much trouble writing my sigma symbol today. Also can't find my whiteout. There it is. You don't really have to get fancy with it. You can just do this. I tend to put like a little line on there, but I mean, you really can just write it backwards like that. So notice that you don't have to start at 1. Okay, you can start at 0. You can start at something other than 1, like this one does, like 2. But that just tells you where to start. So you're going to do 3 times 4 to the 2 minus 1 power. By the way, remember, because of order of operations, we would not multiply the 3 times the 4, right? We would do the exponent part first and then multiply by the 3. And then we'd have 3 times 4 to the 3 minus 1 power, all the way up till we reach our end, which is 5. Okay. So again, I think you might notice a pattern here. So if you do 4 to the first, which is what that would be, right, times 3, that would give you 12. Here you're going to get 4 squared. Make sure you do that part first. So 16 times 3, which is 48. You have to get at least 3 numbers before you know the pattern. So this would be 4 to the 3rd power, which is going to be 64. And then 64 times 3 is going to be 192. Okay, so notice we're definitely not adding. But notice this is actually 4 times more. So if you do 192 times 4, or you just plug it in that pattern, you'll get 768. And the sum that you get when you add all of those up is 120. Okay. So notice that this is actually a geometric sequence. that up. Okay, so when we know that we have one of our specials patterns, which is arithmetic or geometric, we have some formulas for those. So the sum of the first n terms of an arithmetic sequence is going to be n over 2 times the first term plus the last term. Okay. Notice these are infinite series, right? So you could actually keep going forever and ever. So you are going to have to kind of say what sum you're going for. In a lot of books, you'll see an S sub n here. So instead of just a sum for S, they'll actually give you a subscript. Okay, so you might see that too. So let's look at a sequence. And note that this only works for arithmetic sequences, the formula I just gave you. So you do need to verify that that's the kind of sequence that you have before you just, run off and use the formula. Okay. So notice this would be very difficult to do just, with brute force, right? We don't want to have to add 50 numbers together. So we're going to be searching for a pattern here. But before we can assume what kind of pattern it is, we need to write out a few of the numbers. So we're going to do plug in 1, right? So 3 times 1 minus 4 would be -1. Plug in 2, we'll get 3 times 2, which is 6, minus 4, which will be 2. Plug in 3, and we'll get 9 minus 4, which is 5. So I think we can establish that the pattern is probably arithmetic, right? So notice that the pattern is that we're adding 3. But we are going to go ahead and do the last number because we're going to need that for the formula. Okay. So the last number, so notice I said, hey, I don't want to list these all, so I'm going to do ... Okay, but if you plug in 50, you're going to get 3 times 50, which is 150, minus 4, which is 146. Okay. So since the sequence is arithmetic, and only because of this, so since we can tell that this is arithmetic, then we can use the formula of S sub n equals n over 2 times a plus 1 plus a sub n. Okay, so we'll get that S sub 50 would be 50 over 2 times -1 plus 146. And notice that's a whole lot easier than adding 50 numbers together, right? So we would probably use our calculator, but that would be 145 times 25, which works out to be 3,625. Okay. So just like before, if we can identify the sequences as one of our patterns, we have some formulas that we can use. Okay. Okay, so the sum of the first n terms of a geometric sequence have a formula as well. I don't know why I can't write, but I just can't. And the formula is S sub n equals a sub 1 times r to the n power minus 1 on top, and then all divided by r minus 1. Okay, so let's do one of those. So let's say I asked you to find the sum. And we've got I equals 1 to 20 of this sequence. So again, we first need to establish what the pattern is, and then once we do that, if we want to use one of the shortcut formulas, if we can, then we will do that. So if you plug in 1, remember to do exponents first, so you'll get 3 times 2 to the first, so 3 times 2 is 6. If you plug in 2, you're going to get 2 squared, which is 4, times 3, which is 12. Remember, 3 numbers establish the pattern usually. Plug in a 3 and you'll get 2 to the third, which is 8, times 3, which is 24. So I think we can decide that the pattern is that we are multiplying by 2. So just like before, we're going to do dot, 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 and then we're going to fill in the last one. So 2 to the 20th power, that would definitely be something that we would want to use a calculator for, right? So, can't find anything. So let's do 2 to the 20th power, and then of course we also have to multiply by 3, right? So I get 3,145,728. Okay. So if I want S sub 20, I will do the first term, which is 6, times 2 to the 20th minus 1, and then all over the R minus 1. Okay. So what you should end up getting, and you can check your calculator to make sure that I'm correct, is 6,291,450. Okay, so note a couple of things. Note that if D or R is greater than or equal to 1, then the series or the sum will just continue to grow or get larger. Okay. In other words, those values would just keep growing, right? If I asked you to instead find the sum of the first 30 terms, you would expect that sum to be larger. That is not necessarily the case for a sequence where R is less than 1. Okay, so what I mean by that is, let's take the following sequence. Okay, so notice we start off with 1 and we're just halving the numbers each time, right? So note that R is actually 1/2, okay? And then also notice that the terms are getting closer to 0. Okay, so when the terms are getting closer to 0, you're actually adding smaller and smaller quantities as you go. So in general, if your R is something in between -1 and 1, okay, then to use our calculus terms, the limit as n approaches infinity of R to the n power is 0. Okay, that's actually one of the principles of infinite limits when we do talk about calculus, right? So in other words, the more and more you grow in this sequence, actually the smaller and smaller the value gets. Okay, so if you continue to half over and over, you're going to end up with smaller and smaller and smaller pieces. And so we actually have the sum of an infinite series. In other words, we can actually, rather than coming up with an individual sum, we can actually tell what the overall sum is going to trend towards or what its limit will be. Okay, so if R is between -1 and 1, or in some textbooks you'll see R, the absolute value of R is less than 1, then the sum of the infinite geometric series will converge towards something. And the formula will be S equals A sub 1 over 1 minus R. Okay. This only works, again, when you have what we call a convergent series, where the values are converging towards something, in this case, 0. Okay. Where it's getting closer and closer and closer to, the values are getting closer and closer to 0, but you're still adding them up as you go. So let's look at a few examples there. So I want you to find the infinite sum. That looks like the following. So let's do 2 to the negative parentheses I plus 1. Let's do minus 1. I minus 1 power. So just be a little more careful with this. Okay, so if you plug in 1, you're going to get 2 to the 0 power. Well, anything to the 0 power is just 1. Okay. If you plug in 2, you're going to get 2 to the, this becomes 1, right? 2 minus 1 is 1, but then it's 2 to the negative 1. And anything to the a negative power is just a fraction, so this is 1/2. If you plug in 3, you're going to get 2 for the parentheses, right? And then you're going to have a minus sign, so 2 to the negative 2 power is 1/4. And so I'm just going to say dot, dot, dot. I think we're pretty clear that the pattern here is 1/2. Okay, so since this is, number 1, a geometric series, and number 2, since r is less than 1, we can use our formula, our infinite series formula, which is first term over 1 minus r. Okay, so if you were to add up, sorry about that, I didn't realize I wasn't in the view of the window. So if you were to add up all of the terms in the sequence, it's going to get close to first term over 1 minus the r. So it's going to be 1 over 1/2, or basically, remember when you are dividing fractions, it's the same as multiplying by the reciprocal. So you end up getting 2. Okay, so let's see if we can find a few more of those. So find the infinite sum. And let's say that we end up getting some sort of sequence like this. Rather than write it in summation notation, I'm just going to kind of do it quicker than that. So you've got 3 plus 3/4. This would be 3/16. This would be 3 over 64. So it looks like we're just multiplying the bottom by 4, which means we're multiplying the whole thing by 1/4. Okay, so r is 1/4 and it's geometric. R is less than 1. Okay, so that means we can use our formula. So the formula will be first term over 1 minus the r. So 3 over 3/4 is the same as 3 over 1 times 4/3. You could use your calculator, or you get 4. Okay, so again, I just want to try a few of these just to kind of show you how you might see different formats. So what about this sequence? 3 minus 1 plus 1/3 minus 1/9. Anytime you see the signs alternating, you know that your r is negative, or you should know. Notice to get from one term to the next, it looks like I'm dividing by -3. So remember, that means the same as we're multiplying by -3, okay? Which is less than 1, right? And this is geometric. Okay, so since it's less than 1 and it's geometric, we can use our sum formula. So it would be 3 over 1 minus -1/3. Okay, so it would be 3 over 4/3, which is the same as 3 over 1 times 3 over 4, or you get 9/4. Okay, so sometimes you might not get answers that are whole numbers, and that's okay. When possible, I do want you to list those as a fraction. Okay, so 9/4. You could also say 2.25, but I'd just assume have it as a fraction format. All right, so the last one, and then I want to look at some exercises maybe for next time and also kind of introduce your homework. So I wanted to do one where we have a summation notation. Okay, so notice I'm asking you to go from 1 to infinity, which means it's not a finite series, right? It's an infinite series that goes on forever and ever. So first I need to see if I can use my formula, and to do that I need to make sure that it's geometric. So again, if you plug in a 1, you're going to get something to the 0 power, which is just 1, right? And then times 8 would be 8. If you plug in 2, you might need a calculator for this. You would get negative 0.3 to the first power and then times 8. So that's just negative 0.3 times 8, which is negative 2.4. If you plug in 3, you're going to get 0.3 squared, okay, which is 0.09, and then times 8 would be 0.72. So, if you're not really sure, but you would need to divide this one by this one, okay, or this one by this one to try to figure out what your R is. So I'm going to go ahead and do the next one. This is geometric, but it's just with decimals, it's a little bit harder to figure out. So what I mean by that is you can always take 2 consecutive numbers and just divide them. So notice if we do, let's see if I can make sure that shows. Negative 2.4 divided by 8, I get negative 0.3, right? But also 0.72 divided by negative 2.4 is negative 0.3, right? And so is the negative 0.216, sorry, I lost my train of thought for a minute, divided by 0.72, that's also, oh, I did the wrong thing. Punch it in right, and you'll get the same ratio, which is the negative 0.3, okay? So I know this is strange, right? But R is negative 0.3, okay, which is less than 1. It is geometric because we're multiplying by the same amount each time, okay? So if I want the infinite sum, it's going to be first term over 1 minus 0.3. There's a negative sign in there. So it actually works out to be, I'm going to erase this so that it's actually 1 minus negative 0.3. So it's actually 8 over 1.3. And if you divide 8 by 1.3, you end up getting a fraction which is 80 over 13. Okay, kind of a random fraction, right? Or right about 6.158, 1538 rather. So if your answer doesn't come out to be something recognizable, like I wouldn't say 80 over 13 is very recognizable, then we might want to go ahead and assign a rounded decimal for that. Okay, so we have 2 types of sequences, arithmetic and geometric. I mean, there are more, but those are the ones we know really, really well. And then we have a special infinite sum of a geometric series that we talked about today. So if you look at your homework for the week, and again, it's under the same tab. So I want us to look at some of these. Okay. So we are going to talk a little bit more about sequences next time. But for now, I just want you to try to start the homework. Okay, so actually you're not going to get a new homework assignment during the next class. It's actually going to be a continuation of this one. So this is going to be your only homework assignment for the week. Because next week in week 8, we're actually going to take test 1. Okay, so I definitely want you to go ahead and start on this. I am going to make the due date for this a week from today, which would be March 2nd. Okay, like I said, we'll probably cover some of these more word type problems at the beginning of class next time. Okay, but essentially you actually have all the skills that you really need to be able to do this homework assignment. Okay, and so on Thursday we're going to start the class looking at some more word type problems using sequences and series. And then we're also going to look at a common infinite sequence in picture form, which is called a fractal. So that's what we'll be doing on Thursday. And unless I hear otherwise, I'm expecting that we'll be in class on Thursday. Okay. So like I said in the email before, you're going to take notes. And what I'd like you to do is I'd like you to send me your worksheet. Okay, so like included in your notes, because I asked you to pause the video and blah, blah, blah. Included in your notes, I want you to send me some snapshots of this. Okay. And then also where you took the notes. Okay, so it's like the handout that I gave you for the week or for the day, sum of consecutive numbers, and then also the notes we took. So there is a folder in D2L, and it's literally called something like lecture notes on 223 or something like that. Okay, so I am going to take a grade based on did you participate in the class virtually. That's really the only way that I'll know if you were here or not, since the class is so strange today. So make sure you upload me that. That's due by the end of the day today, but the homework that we're looking at right here on the screen, that's not due until a week from today as usual. Okay. All right, well, email me if you have any questions or concerns, and I hope to see you guys on Thursday.